Good afternoon, Professor.
Hello, nice to see you.
Excuse me, Professor. I want to ask one question about rotational motion. Recently, I watched a lecture from Professor Levin from MIT, and was talking about that some of rotational energy can be converted into kinetic energy in some machines or cars with flywheel.
With what? Can you repeat?
A flywheel.
Flywheel. You mean you mean some mechanical like energy accumulator?
I think it's like a converter, of rotational energy to kinetic energy.
Yeah, there are some concepts of accumulating energy when, like, usually we're tested on some trucks, like big cars, when part of kinetic energy, well, let's say part of potential energy while cars were moving down hills was transformed in kinetic energy of the, let's call it mechanical accumulator, which is like some heavy spinning, fast spinning disk. And then in the contrary, since this disk could spin for a long time without much of energy dissipation, there's like minimum friction. You could convert this energy while going uphill somewhere in other location by connecting it with some gear to the actuator which spins the wheels. By the way, there are concepts of larger scale mechanical accumulators which actually do not use spinning objects, but it's a system of heavy blocks which can be lifted up and put back down, and depends on the consumption of energy in the grid. These heavy blocks can be picked up on certain height, while there is, for instance, during the day when there is no need in a lot of electrical power, and it's still produced by, let's say, solar panels or nuclear power stations, which cannot be well controlled. So this excessive electrical energy, which is not in demand by industry and population, could be used to pick up those heavy blocks. And then when there is a demand in the evening, they just let these blocks come back to initial position. And while they moving downwards, they spin generators, which actually is the same engine, like it's DC actuator, which can work both as electrical actuator and electrical generator. Just depends if you apply some current, it produces work, mechanical work, so you can pick it up. And then when you let this weight go down, it spins the this DC rotor and the direct current rotor, and it generates electricity. So it's nowadays they try to implement some concepts of machine learning and artificial intelligent systems to do it in the most efficient way, really to know exactly the best time when you can take energy from the grid to pick them up, and then the best time when it has to be generated, like this accumulated energy has to be used. So it shouldn't be controlled by some humans. And now the biggest challenge to scale it up. But there are companies in the United States which are working on this quite successfully. They got investments of about like $100 million, which is quite a lot. So we'll see. Maybe lithium-ion batteries will not be just only one option for accumulation of electrical energy, which I believe should be diversified, shouldn't rely only specifically on them, while they are still probably nowadays the best option which can be proposed on a large scale. You're welcome. Oh, that's, if you have any questions, we can discuss them. It's not a problem. Okay, guys. So I believe everyone who wanted is already here. And we need to proceed further with speed of sound. We need to finish this derivation, if you remember. So we stopped last time our discussion at the point when we defined the left and right sides of the impulse momentum theorem. And the left side, which is for impulse of the excessive force, which pushes the piston and selected volume of the gas from the left. So it's given by this equation. And the change in momentum of this small volume of the cylindric volume of air is given by this equation. So now we just equate the left and right side and get the following picture. So A, B, V, X divided by V. So A is area, B is this bulk modulus, Vx is the velocity which the piston has, and also which gained the volume of considered volume of the gas. V in the denominator, it's velocity, speed of sound. And then we have delta t, like time interval, and this is equal to rho, which is density, speed of sound, then Vx, A delta t. So we cancel out quite a lot here. All these parameters go away, and Vx also. So from here, we get that velocity, like speed of sound, is equal to square root of b divided by rho. So we can draw some analogies to the speed of mechanical wave in which is spread along the string. If you remember, for that we got equation which is equal v square root of t divided by mu. So t is tension in the string and mu is the linear density. So you see quite of a good correlation between these two equations. In the nominator, for both cases, we have some elastic features of the medium, and in the denominator we have density of the medium. So in this case, it's like bulk density per cubic meter or cubic centimeter, and for the string, it's linear density, like per centimeter or per meter. But they are very, very similar, and that's another example which highlights the common nature of all types of mechanical waves, which we experience in different environments. Okay, so I guess before we proceed further with the determining the power of energy which is spread together with sound waves and its intensity, we need to come back to one fact which we derived previously. You may remember we have shown that change in pressure, like maximum value, like amplitude value, was given as a product of B times S maximum. S is displacement, maximum displacement of the element of the gas, and wave number K. So this equation is good, but more practical one if we relate change in pressure and maximum displacement. We are not this parameter B, but we are density of the gas, since it's more commonly accessible information, like parameter. So in order to do that, now when we know the equation for the speed of sound, which is equal to V divided by rho, so we can express B from this equation will be rho V squared, and substitute here. So we end up with delta P maximum equal to rho V squared as maximum K. Now let us recall what K is. So K is the wave number, and this is equal to 2 pi divided by lambda, which is wavelength of the sound wave. And now let us multiply and divide by frequency, and we get the following. It will be 2 pi times frequency will be angular frequency, omega, and lambda times frequency. Do you know what will be lambda times frequency?
Velocity.
Yeah, speed of sound, can call this V. Yeah, it's kind of how many times per second how many wavelengths per second the front of wave is moving forward. And since this wavelengths we measure in meters, and this will be meters per second, so this is speed or velocity. So now we can again substitute K with this expression. Then we can get the final expression for the maximum change in pressure. Rho then will be V, because we cancel like this square and this V. Omega S maximum. Okay. Now we have this convenient and simple relationship between change in maximum change in pressure and maximum displacement. So we will later come back to this point when we consider the intensity of the sound waves. Okay, so now we are done with the speed of sound. By the way, just some additional information. It definitely, if we consider sound, for instance, spread of sound waves in air as most common case for our everyday experience, this speed of sound will depend on temperature, because it will change the density of the air and also its elastic properties. So it's usually considered around 331 meters per second, the speed of sound under normal conditions at 0 degrees of Celsius. And at room temperature, something about 20 degrees of Celsius, about 340 meters per second. So kind of an interesting option to determine, to estimate the distance to the thunderstorm. If you see the lightning, for instance, you count after lightning number of seconds before you hear the thunder, and then just divide by 3. You can estimate the distance of the thunderstorm to your location, assuming that light is moving. Like, so you see lightning instantly without any delays. So that time between lightning and thunder is the time which sound wave takes to travel along the distance between you and thunderstorm through atmosphere. Okay, now let's go and derive equation for the power of spread energy, like how much energy is carried by sound wave per unit time. And for that, we need to consider again this familiar to us system with a cylinder and a piston, which will move back and forth. We'll get some harmonic oscillator with certain angular frequency omega. And here we consider some small volume of gas with some, let's say, dm, very small mass, which also will follow the movement of this piston, and the speed of the piston, and thus speed of this small volume of gas will be Vx, as we considered previously. So now I will write actually power, in order not to be confused with pressure, because we use capital P for pressure. So let's write power it will be considered in our case as a scalar product, like dot product of two vectors, force vector and this velocity vector, Vx. So we know that scalar product of force and displacement gives us work, which actual energy. And since it's displacement per second velocity, it will give us power, work done per second. So with this, it's clear. And we also need to take into account that vector of the force, which moves this piston and disturbs the system, is parallel to the velocity vector, Vx. And that's why this product can be equal to the product of two absolute values of these vectors, like F times Vx. Since angle is equal to 0, cosine of 0 is unity. So let us write this down. So this will be this force, which force it will be. So this force is some excessive pressure as a function of position and time, which is applied from the side of the piston, times area of this base of the cylinder, which we consider. So it will be delta P x t times A, and this we need to multiply by the absolute value of the velocity, and this will be nothing else as a partial derivative of the displacement function, again as function of x and t, but now we care only change by over time. So it will be d as a function of x and t over dt. Okay, so let us now write in more details this equation. So for the pressure, we can put the value for the maximum change in pressure times sinus kx minus omega t. So it will be, and we remember that change, like maximum pressure change, delta P maximum is equal to this. So we want to express it via in terms of maximum displacement. So to have the same terms for the both products, components of this product. So instead of delta P max, we write rho V omega S max times sinus kx minus omega t. And this we need to multiply by A. I forgot. Let's put it here, area. Now we need to multiply this by the derivative of this s as a function of xt. So maybe let's write the derivative first to be, and then we will take the derivative. So d here will be s maximum times cosinus kx minus omega t divided, or no, not like over delta t. Okay. So we can rewrite this first part without changes and then take this derivative. It will be rho v omega s maximum a times sinus kx minus omega t times derivative. Okay, so what will be derivative? Well, derivative of cosinus will be minus sinus x, and then we have derivative over t, so it will be minus omega times minus omega, so minus and minus will give us plus, and we will end up with omega s maximum sinus kx minus omega t. Okay, so we see that we have here sinus and here sinus, so we just factor out this sinus. I mean, it's like sinus square will be. So maybe we can squeeze it here. It will be, finally, we get rho times v times omega square. We have omega here and here times s maximum square times a and times sinus square kx minus omega t. Okay, so now we have expression for some for the power which is carried by unit time through area A with a sound wave. Now what we want to do, we need to get some average value of this power because it gives us as at a given like a function of time, we want to get some average value per one period to get a sense what actually power will be in one period when all cycle, all oscillation is finished. That's why we need to take average value of this function which we derive in the time range from 0 to t, like capital T. Let's rewrite this final equation on the next slide, and let's do this integration in order to get the average value. So power equal to rho times v times omega square times s maximum square times a times sinus square kx minus omega t. Okay, so we see that here all these components are let's call it coefficient, it's a constant. And what can change over time is only this sinus squared. So that's why we need to determine what will be the average value of sinus squared kx minus omega t when the time interval is from 0 to t, which is the period of the oscillation, which forms the sound wave. So average value of any function is equal to 1 over, in the range from a to b, will be 1 divided by b minus a, integral from a to b of this function as some independent variable x dx. So we need to apply this concept to sinus square, and in order to make it more convenient, because it doesn't matter at which x we do it, it doesn't change its, we consider that it doesn't decay or increases, so it's constant at any x. We can consider for convenience x equal to 0, and then we will end up with a function which is sinus square kx minus omega t. X is equal to 0, then this will be 0, and we have sinus square minus omega t. So here at this point we need to emphasize that according to trigonometry, sinus minus x is equal to minus sinus x, and since we deal with a square, it actually doesn't change much. So sinus square minus x is equal to sinus square x. So taking this into account, we can write here that it will be equal to sinus square omega t. Oh, yes. And now apply this concept for the average function. Let's get the average value from 0 to t. So this will be 1 over t integral from 0 to t sinus square omega t dt. Okay, so at this point we need to find some other form for this function in order to be able to integrate this. So again, from the geometry, we can write sinus square x is equal to 1 minus cosinus 2x divided by 2. So this is another equation which we need to use here. So based on this, we can write that will be 1 over t times 1 over 2 integral from 0 to t dt. That's when we substitute sinus square omega t with 1 minus cosine 2 omega t divided by 2. So we have two integrals minus minus 1/2, then integral from 0 to t cosinus 2x, oh, sorry, not 2x, 2 omega t dt. So with the first integral, we don't have problems for sure. With the second one, we need to have the same value like behind d, like the same variable as in the argument of the cosines. So for that, we can multiply and divide by 2 omega. So we will get 2 omega here and put 2 omega here. So actually times 2 omega. Now this will be equal to 1/t. We get this integral already. It will be t/2 from 0 to t minus 1/4 omega t. So we open this parenthesis here times this integral of cosine will be sinus. So it will be times sinus 2 omega t from 0 to t. Okay, so here the first integral, we will get t divided by 2t, so it will be just 1/2. Then minus, let's see what we get here. We know that omega, angular frequency, is 2 pi divided by t. So omega times t will be 2 pi divided by t times t. And this is 2 pi. So it's 100, equivalent of 180 degrees. And at this angle, sinus is equal to 0. So we actually minus 0, and this will be 1 divided by 2. So this is the average value of sinus square omega t in the interval of 0 from 0 to t. So now we can just multiply this constant, which we have, by 1/2 and get the power which is spread through the area A because of spreading of sound wave. So let us write it already on the second slide. So power, let's call it average per lambda, or maybe to be more consistent per t, doesn't matter, but will be 1/2 times rho v omega square s maximum square times A area. So since we kind of operate with more specific parameter as power, because it depends on air, so for that purpose we can use intensity, and this is power average divided by area. This is 1/2 rho v omega square as maximum square, and there is no a because we divided it by a. So we see that this intensity, similar to previous waves which we considered in the moving along the string, is also proportional to the square of frequency and maximum displacement, its amplitude. So as I mentioned before, this concept that intensity is proportional to square of frequency and amplitude is true for very broad spectrum of different kind of mechanical and even electromagnetic waves, even beyond this. So we also can express intensity in terms of maximum change in pressure. As you may remember, we derived at the beginning that maximum change in pressure is equal to rho times V times omega S maximum. So we can express this product from here and take it to the second power and substitute in this equation for intensity. So it will be omega S times S maximum is equal to delta P maximum divided by rho V. And if we take it to the second power, will be here square and here square. Okay, so if we now substitute it here, intensity in terms of change of the maximum pressure will be 1/2 times rho V delta P maximum square divided by rho V square. So these and these cancel out, and we get final expression delta P square maximum divided by 2 rho times V. So yeah, we can now, based on what is given, express intensity of sound wave in terms of either maximum displacement or maximum pressure. Good. So far we were considering sound wave which is spreading along one dimension, because we consider this cylinder, and obviously it is possible for sound to move along the cylinder. So we have kind of one-dimensional direction for the spreading of this sound. However, in more realistic cases, when we don't have any restrictions, we can consider some point source of sound. And if we have some isotropical environment, means environment which possess the same properties in any direction, we will end up with some spherical sound wave. So if we look at the cross section, we'll look something like this. So all these like arcs, which are spreading in all like parts cross section of a spherical waves, they are some geometrical position of points which possess the same phase of sound wave, and they are called wavefront. So each point at this wavefront, they possess the same phase. And the radial distance between two adjacent wavefronts, which have the same phase, like this one, will be the wavelength, lambda. So radial distance between two adjacent wavefronts with the same phases. And when we draw some straight lines from the source, like outwards from the source of the sound, perpendicular to the front of the wave, fronts of the wave, they show the direction of spreading of sound wave and are called rays. So in this case, since we have different geometry, we need to take into account when we want to calculate intensity, we cannot just divide by area of some base of cylinder, which we had some model system at the beginning. So we need to deal with the area of a sphere, which is defined by the given wavefront. So let's say if we want to determine light intensity here at a distance r, so let's say this is radius of this sphere of spherical wavefront, then we need to take into account the area of this sphere with the radius r and use this when we divide our average power by this area. So in this case, when we have spherical wavefront, intensity will be also equal to average power per one period divided by area. So everything is the same, but in this particular case, we use area of the sphere with radius r. It's at some distance r, where we are interested to calculate the intensity of the sound. So that will be average power per period divided by area of this sphere surface will be 4 pi times r squared. Okay, so I think that with the intensity and power of sound waves, we are done. And next discussion, we will continue with sound, introducing such a parameter as sound level, taking into account the fact that human ears can hear and detect sounds with very broad spectrum of intensities from 10 to minus 12 watt per square meter up to few watts per square meter. So you see it's like more than 12 orders of magnitude. So that's why it's convenient to operate with some parameter, which is sound level. We will discuss this. Then discuss and explain the Doppler effect when we hear different frequencies of the same sound source when it approaching us or going away from us. we'll get some equations for this change in frequency which we detect. And at the end will be a kind of interesting topic of supersonic motion, when we have some source of sound which moves with speed higher than speed of sound in this environment. We'll try to understand how we need to approach this analysis of such source of sound, and we'll introduce this shock wave, and also how we can calculate the spreading of sound, taking into account the fact that the source of this sound is moving faster than the speed of sound in the environment. Okay, so this is the plan for our future discussion. Now I believe we are done. And with this, like with our next discussion during on Friday, we will actually finish studying mechanics, and starting from Monday we will go into molecular physics and thermodynamics. Okay, any questions?
Excuse me, Professor.
Yes.
I have two questions. The first one is about the perpendicular lines to waveforms. Could you briefly explain again what they are?
Oh, so they're called rays, and they define in a given direction where they are drawn the direction of spreading of the sound wave. So if you consider only this kind of small part of the wavefront, this ray is just a direction, since it's perpendicular to the wavefront itself. It shows where the vector v is directed, which is speed of, actually in this case it's velocity of sound wave propagation in the environment.
Okay, thank you. And next question is about the intensity. Should we use always the average power while determining the intensity?
So if you want to get some like total, so we use average power along this one period because we want to know what is total energy per second is carried by the sound wave during one period. If we take some instantaneous power, I mean, it could be that there is some requirement to calculate specifically power at given, some instantaneous power at given time, but that is not really characteristic of the wave itself, or sound itself, because it can be any time. So it can be larger intensity or lower intensity, since our pressure, change in pressure, goes from maximum value to 0, then goes to maximum value again. So means that if, for instance, you calculate power at time when the change in pressure or maximum displacement is 0, then it will be 0. However, we still hear this sound. So in order to give some characteristic feature of the sound, we need to integrate the power over whole period, and then we know how much energy per second is approaching our ears or some other detectors, and that is some characteristic of the sound wave.
Okay, thank you very much.
Some instantaneous intensity which doesn't characterize the wave itself. But it also makes sense, so you can calculate it at a given time, at a given phase. However, it doesn't describe, it's not a parameter of the wave, it's of the sound wave. Is it clear for you?
Yeah, now I got it.
Mm-hmm. Okay, good. Thank you for attention. Have a good evening. And I'm waiting for you on Friday when we will finish our discussion on sound, specifically with supersonic cases. And actually it will be the end of mechanics in our course. Okay, guys. Bye-bye. Take care.
Thank you. Have a nice day. Goodbye.
You too.